So let us continue with the topic of chromatography and how to model this particular packed bed system and what are the issues while modeling. So typically if you look at a chromatography, you are going to get a Gaussian type of peak leaving the column, and this is called the retention time, the T naught, and this is the maximum concentration it reaches. And if it is a normal distribution or if it is a Gaussian distribution, then we said this is the equation for a Gaussian distribution. You have a C equal to C naught exponent minus T by T naught minus 1 whole square divided by 2 sigma square. Now T naught is your retention time, and the standard deviation for this Gaussian distribution will be T naught sigma. Okay. So making use of that, we brought in the concept of number of theoretical stages or theoretical plates. So the theoretical plates or theoretical stages is connected to sigma in this particular fashion. Sigma square is equal to 1 by n. So if the sigma becomes smaller and smaller, n becomes larger and larger. So sigma is related to standard deviation by this equation, T naught into sigma is equal to standard deviation of the Gaussian curve. Okay. So if the Gaussian curve is very sharp, then your number of theoretical plates is going to be very large, and if the Gaussian distribution is very broad, then the number of theoretical plates you can say is less. And then you also have a relationship between C naught and Cf by this equation. And then later on we also looked at another equation which connects the retention time T naught with the several parameters, the operating parameters as well as the chromatographic column parameters, like epsilon. Epsilon is the porosity of the packed column, V is the volume of the packed column, Q is the flow rate of the continuous phase. Now K is the equilibrium constant. Okay. If it is a liquid system, we used to call it partition coefficient, otherwise we can call it an equilibrium constant. So if you incorporate all these, then equation for C becomes like this. Okay. So you have here you have the number of theoretical stages, and then here you have the T naught which is the retention time, and similarly we can have an equation for retention volume also, where you have V naught is the quantity of the liquid that needs to be collected downstream of the packed column so that it reaches the maximum or the peak. Okay. So we use these equations quite a lot, and we did a lot of mathematical derivations and design calculations. We will look at them again once more in some of them, because this is a very important set of equation which describes the performance of a chromatography. We later on introduced something called error function. Okay. This is also called a Gauss error function or a probability integral, because it's an integral between limits, between two limits. Okay. So Fx or the error function of x is given by 2 divided by square root of pi integral 0 to x e power minus t square dt. So if you look at the function, it looks like this. No, it looks like a sigmoidal curve. So between 0 and 3, it starts from the value of 0 and then it goes up and saturates at 1, and in the negative direction again it starts from 0, goes down in the negative direction and saturates at -1. So there is a table which gives a numerically integrated values for Fx for different values of x. You can see that when x is equal to 0, the error function of x is equal to 0, and it keeps going up initially sharply as a representation of this, but then later on it sort of stabilizes, peters out. Okay. And then it reaches a value of 1. So beyond a point around 0.15 or 1.6 or 1.7, you can see the error function of x is almost close to 1 actually. Now this particular table was taken from a Wikipedia website. So for any value of x, we can calculate the error function from this particular table. So this equation, this table is going to be very useful in calculating yields. Now imagine a situation, in fact this problem we did that in the previous lecture as well. So imagine a chromatography peak like this. At 170 minutes you have a concentration like this, and the retention time is 190 minutes. Now we want to know what is the yield at 200 minutes. That means if I collect the sample up to 200 minutes, what is the yield of this particular protein. Now many things are given here. The T0, that is the retention time, is given, and then you are also given some concentration value C at a particular time t. So making use of this, what can we do? We can calculate sigma, and then using sigma we calculate the yield at 200th minute. So if you look at this equation, we know C, that is 0.0063, we know C0, that is 0.0152, and we know T0, which is 190, and we know T, which is 170. So by substituting all this we can get a value for sigma. Okay, so that is how you do that. By substituting all this into the equation we get sigma. Now we go to the yield equation. I hope you remember the yield equation. Yield is equal to 1 by half multiplied by 1 plus error function of T by T0 minus 1 by square root of 2 sigma. Now why does this 1 comes in? Because we are going to collect sample up to 200 minutes, which is greater than the retention time 190 minutes. So if we keep collecting up to 190 minutes, the yield will be 50%, that is 0.5. So if you are going to collect beyond 190 minutes, obviously the yield is going to be greater than 50%. That is why this particular term comes in here. Okay, now we know sigma calculated from the previous case, we know T0, which is 190, T will be your 200, so you can substitute here, so that will be your x. So you, from the table you can calculate Fx, substitute here, and you get the value for the yield. So easy it is. So by plugging in all these numbers we get the x, hence the Fx. Okay, so straightforward, very simple actually. So it comes to yield is equal to 0.8, that means 80% yield. So if I keep collecting sample up to 200th minute, the yield of the particular product is going to be 80%. This is not talking anything about the purity, please note that we are not talking about purity, because there could be other components also coming in which may reduce the purity. So if there are several components and if I keep on collecting one component, then the purity may be going down, whereas if I want a very high pure material, obviously I am going to sacrifice on the yield. Okay, now let us look at a two component system. You have a protein P, you have an impurity I. I did introduce this problem in the previous class also, I am repeating it again so that you are well conversant with this particular system. Now imagine you have a Gaussian type of distribution for protein P, the T0 or the retention time for the protein is 6.42 hours. Now the impurity also has a Gaussian distribution, but it is coming at 7.6 hours. Okay, so at 6.42 hours you have only the protein, whereas the impurity is 0. At 7.6 hours you have some amount of protein and you have impurity. At 7 hours you have very little of the impurity and predominantly more of the protein. Now how do you solve this problem? Now you will have two different Gaussian distributions, so, and you have two different retention times, so obviously you are going to have two different sigmas. So how do you calculate those two sigmas? We can calculate from these places. We know that T0 for the protein, we know the T0 for the impurity, correct, and then we also know the concentration values at different times. At, you know, the C0 for the protein, you know the C0 for the impurity, we also know the concentration at some other intermediate time. So we can again use the equation C is equal to C naught e power minus T by T naught minus 1 whole square divided by 2 sigma square. I hope you remember this. So for the protein T naught will be 6.42, correct, and C by C naught will be 63 by 82 and T will be 7. So we can calculate sigma. Similarly for the impurity C by C naught will be the same here as this divided by this, that is this value by 43, and T naught will be 7.6 hours and T will be 7. Again you can calculate a sigma for the impurity. So you are going to get two different sigmas like this, sigma for the protein, sigma for the impurity. Now yield is given by this error function equation, okay, where half into f of T by T naught minus 1 divided by square root of 2 sigma minus f T dash by T naught minus 1 divided by square root of 2 sigma. So if you are collecting the product between the time T dash to T, then this is the equation for yield, okay. And the purity in this two component system is going to be concentration maximum into yield divided by summation of the concentration yield for component 1 and concentration yield for component 2. So this is a two component system, okay. So now you know the sigma for the protein, you can substitute it here, okay, and you know the sigma for the impurity you can substitute here. So you will have two equations separately, so we can get yield as a function of time as well. So the protein yield may build up and then it sort of flattens out, and then the impurity yield may build up and then it sort of flattens out, okay. This is how it will look like actually. So if I go further, I will be collecting some amount of impurity as well, whereas if I am here I am going to get pure protein, whereas if I travel a little bit here I am going to bring in some of the impurity also in my product. So the purity of the protein is going to go down, okay. We also started introducing this particular concept which is called the continuous packed bed model. So if we consider our chromatographic column as a packed bed of consisting of a tubular design, it is a continuous system. So there is an axial z axis, okay. Now the solute is moving with the continuous phase from one end and then it just comes out from the other end. You have the packing material or the stationary phase uniformly distributed, there is a voidage. So in the void space you have the liquid contains your solute is also adsorbed on the packed material, and the adsorption process could be controlled by several different types of mechanisms. We will talk about these mechanistic aspects later. So we have the solute moving in with the solvent or the mobile phase from one end to the other. So solute is getting carried because of solvent flow, the solvent is flowing at certain velocity. The solute is moving because of diffusion or dispersion, because there is always going to be diffusion like your Fick's law of diffusion. I hope you all remember what is a Fick's law. And then this solute is going to get accumulated in the voids of the interstices of the bed. That means the voids of the interstices of the bed is going to contain your continuous phase solvent. So solute is going to be present there, and you are also going to have a solute accumulated or adsorbed onto the stationary phase, that is the solid material. So you have two accumulations, okay. So if you combine all these you are going to end up with a partial differential equation. This is a typical partial differential equation. So on this side, that is on the right hand side, you can see you have a diffusion term here, this is called the axial diffusion or dispersion term, and then this is going to be a d square c by d z square. This term comes because of diffusion, and then you have a flow term, that means you are going to have a solute movement because of the flow. Now z is the axis, okay. So you have a term coming because of the diffusion of the solute in the along the axis, and you have a term here which talks about the flow of the solute with the bulk solvent. On the left hand side you have two accumulation terms. One term corresponds to the accumulation in the void space, that is in the continuous phase, another term is because of the accumulation in the solid phase, okay. So you have two terms. Now C is the concentration of the solute in the interspecies, or C is the concentration of the solute in the mobile phase, whereas Q is the concentration of the solute in the adsorbed or in the stationary phase, okay. Now epsilon is the voidage, that is voids, and 1 minus epsilon is obviously the amount of solids present, okay. So there has to be a relationship between C and Q, and that relationship may depend based on the type of mechanism that is operating, okay. You can have different types of mechanism which will determine what will be the relationship between C and Q, okay. So you need to have a very simple mechanism, then you will be able to solve this equation analytically, otherwise we may have to solve numerically. Now you can consider several approximations if you want to solve them analytically. So now what are the approximations? We can assume that the diffusion or dispersion is negligible, that means d square c by dz square could be omitted. We could assume that the accumulation in the void space is also negligible, okay. Accumulation in the void space is also negligible, okay. So then what do you end up with? You will end up with the accumulation on the stationary phase, that is the solid phase, and this arises because of the flow of the bulk material, bulk solvent, understand. So we have neglected the accumulation in the void space or the mobile phase, we have neglected the dispersion, so we end up with the simpler looking equation. Now you needs a lot of initial conditions. The initial conditions are there are no solute adsorbed on the packing when the time is 0 or less than 0, because we have not injected any solute, we inject solute only at time equal to 0. So at any place inside the column when time is less than 0, Q equal to 0, and at t equal to 0, that is at 0 time, we inject the solute at the entrance of the bed, because only at the entrance we are injecting. These are the initial conditions, but still it is not enough if you want to solve this particular partial differential equation, okay. So we need to have some relationship between Q and C, otherwise we will not be able to solve that. So that means we need to have what type of mechanism is operating. There could be a lot of things happening inside, physical processes happening. Because it is a chromatography, we will assume there is no reaction, so there but there are a lot of physical processes taking place which may be controlling, which determines the relationship between Q and C. So what are the various physical processes that may be operating here? For example, mass transfer from the bulk of the solution to the surface of the particle. So you have the continuous phase flowing, that is the bulk, that is a liquid, whereas your stationary phase is a solid, and whenever there is a solid and a liquid interface, there is going to be a mass transfer resistance for the solute to diffuse from the bulk onto the surface of the solid or the stationary phase. So there is going to be a mass transfer, number 1. Number 2, if there are pores in your stationary phase, there could be diffusion of the solute into the pores, so that could be controlling. If there is a reaction taking place, then the reaction also may be controlling, but in a normal chromatographic system we shall completely omit this. So these two things may be happening. One is the mass transfer from the bulk of the solution to the surface of the catalyst or the solid material may be controlling, or the diffusion of the solute from the surface of the stationary phase into the pores may be controlling. So depending upon which is controlling, you may have different types of relationship between Q and C, okay. So you need to understand that depending upon which is the important equation or which is the major controlling factor, you may have different relation between Q and C, and if you know which is controlling and if you have some sort of a relation between Q and C, then it will be possible for you to solve the partial differential equation which we talked about in the previous slide, namely this, okay, which is 1 minus epsilon into dq by dt is equal to minus v dc by dz, where v is the velocity, epsilon is the voidage, q is the concentration of the solute which is bound to the stationary phase, c is the concentration of the solute which is present in the mobile phase, t is the time, and the z is the axis. So what it means? It means the concentration varies along the axis of the chromatographic column as well as the concentration varies as a function of time, okay. So if the mass transfer of the solute from the bulk to the surface of the particle is controlling, as I mentioned, this is a solid particle and the bulk solution is a liquid. So whenever there is two different phases coming in this particular case it is a solid and a liquid. If there is a gas, then there could be a gas and a solid. If there is a absorption where you can have a gas and a liquid, again there is a two phase system. Any two phase system will always have an interface and there will be a resistance for a particular component to move from one phase to another. It may be very slow, it may be fast, but still there is a resistance. So in this particular case we call it the mass transfer resistance, the movement of your solute from the bulk to the surface. So we can assume the concentration of the solute at the surface at C star and the concentration of the solute in the bulk is C. So what does it mean? The driving force here is C minus C star, okay, and the equilibrium interaction is between Q and C star, not between Q and C. Please note the adsorbed species is not seeing the concentration C, but it is seeing only the concentration C star, and so the driving force is C minus C star. So if the mass transfer of the solute from the bulk to the surface is controlling, then you can consider equation like this: 1 minus epsilon dq by dt is equal to KL A into C minus C star, where C is the concentration of the solute in the bulk, C star is the concentration of the solute on the surface of your particle, KL is the mass transfer coefficient, A is the packing area per bed volume, and epsilon is your voidage, Q is the concentration of the solute on the stationary phase, okay. So if the mass transfer is controlling, what this equation tells you is the accumulation of the solute in the solid phase is exactly equal to the amount of material which is moving from the bulk to the surface, okay. Okay, so with that equation you will be able to solve the partial differential equation. Now let us again go back to our Gaussian distribution or normal distribution for our chromatographic peak. So we said the chromatographic peak looks like a Gaussian shape with the retention time and a standard deviation. Now the standard deviation can keep changing depending upon the type of mechanism. Okay. For example, the standard deviation, in the previous case we talked about mass transfer controlling. We said KLA is the mass transfer rate, C minus C star is the driving force, right. So in such a situation then your sigma square standard deviation is sigma into T naught, where T naught is the retention time. So if mass transfer is controlling, then sigma square could be equal to V divided by KLA into L. V is the velocity, L is the length, KLA is the mass transfer coefficient. Okay, KL is the mass transfer coefficient, A is the area per unit volume, that is interfacial area per volume actually. Now A in a packed bed of spherical particle is approximated like that. A is equal to F dash by D into 1 minus epsilon. D is the diameter of the spherical particle and F dash is 6 for if it is spherical, and it is equal to 4 for cylindrical type of particle actually. Okay. So A is the interfacial area between the two phases. In this particular situation it is the bulk liquid or the mobile phase liquid and the stationary phase solid. Okay. So if you are decreasing particle size, we are increasing mass transfer coefficient, correct, because the A comes below. Okay. Decreasing particle size increases mass transfer coefficient. Okay. So ideally it will be very nice to have very small sized particle, but then in a packed column if you reduce particle size you are increasing the back pressure. That means you need to have pumps which can deliver very high pressure. That is why if you have HPLC type of systems where the particle size are in micron range, the pressure developed by the column is so high that you need a very high pressure pumps. Increasing velocity and particle size increases sigma. Okay. So if the particle size increases, sigma increases, if the velocity increases also, sigma increases. So if sigma increases, obviously the width of that Gaussian pulse also increases. Increasing column length decreases the width. So if I have longer column, I am having more number of theoretical plates, so the width of the pulse also decreases. Now in addition, the standard deviation changes because of dispersion of flow in the column due to polydispersed packing material, because although they say we have uniform sized particles packed inside a chromatographic column, there will be still a distribution of sizes on the average diameter, you know. So there will be a plus or minus 10% of the average diameter. So the polydispersity also will affect the standard deviation. Now let us again go back to the same chromatographic output like this. Now the retention time is 93 minutes. Okay. Now I want to calculate what is the time required if I want to have 90% yield. This is a very important problem. I have a protein in a mixture, I am running a chromatography and I know the retention time, I know the standard deviation. I want to know how long should I keep collecting this effluent so that I get a yield of 90%. So it is a very important problem. Now the standard deviation for this system is 12 minutes. So the retention time is 93 minutes, standard deviation is 12 minutes. So how do you calculate yield? Okay. Now so I know T naught, I know standard deviation, so I can calculate sigma 12 by 93. Now taking this I can substitute into the yield equation. Now the yield, of course I want 90% yield. So obviously if I am collecting sample up to the retention time, my yield will be 0.5. So anything above 93 minutes my yield will be above 0.5. Okay. So what equation do I use? This is a general equation for yield, which is half into F T by T naught minus 1 divided by square root of 2 sigma minus error function T dash by T naught minus 1 divided by square root of 2 sigma. But because my yield is going to be more than 50%, I will use the simpler equation, okay, half into 1 plus error function of T by T naught minus 1 divided by square root of 2 sigma. Now in this equation yield I substitute as 0.9, T naught is 93, sigma is given by 12 divided by 93. So if I substitute all of them, the only unknown is T. So from this I can calculate what should be my time until which I keep collecting the effluent so that the yield is 90%. Okay, so first I calculate sigma, then I substitute there. So by doing this, and how do I calculate Fx? If you remember, I showed you a table where given a x I can tell you what is the error function x. Okay, so if I keep collecting up to 115 minutes, my yield will be 90%. So you see, this is a very important problem, especially if we are wanting to collect as much as the metabolite that is present in my broth as possible. Okay. So I use the same equation, and I have T, that is the only unknown, rest of the things are known. So T comes out to be 115 minutes. Okay, let us look at another problem where we are looking at the type of controlling mechanism. Okay. So initially my mobile phase velocity is 30 centimeter per hour, now I am doubling it, that means it becomes 60 centimeter per hour. So I want to achieve this 90% yield. Now how long do I wait? Now the controlling mechanism is internal diffusion, the process is controlled by internal diffusion. So if the process is controlled by internal diffusion, anyway sigma square is going to change, okay, or the standard deviation is going to change, or the width of these peaks are going to change, right. Now if the process is controlled by internal diffusion, that means diffusion of the solute inside the pores of the solid matrix, then sigma square is proportional to V, the velocity, d square, d the particle size, particle diameter, and L the length. Okay. So here I am doubling the velocity from 30 to 60, so obviously sigma square will get doubled, or sigma will be square root of this number. Okay. So I will get a new sigma, I know the old sigma, so with the new sigma I substitute, so I should get a different time. Okay. So now I have doubled, so my retention time was originally 93 minutes for 30 centimeter per hour, now I have doubled it, so my retention time becomes half of that, 46.5 minutes. Okay. Now sigma square is proportional to V d square by L, that means sigma is proportional to V raised to the power half. So now originally it was 30 centimeter per hour, now the velocity has become 60 centimeter per hour. So originally my sigma was 0.129, so now the sigma will be 0.182 because sigma is proportional to V raised to the power half, velocity has doubled, so you have to multiply by square root of 2. So your sigma has gone up from 0.129 to 0.182. Now I go back again to the yield equation, I take yield equal to half of 1 plus F T by T naught minus 1 divided by square root of 2 sigma. Now T naught has gone down, remember I have doubled my flow rate, so T naught has gone down from 93 to 93 by 2, and sigma has gone up from 0.129 to 0.182. So I will substitute new sigma, I will substitute new T naught, and again I calculate this error function, and yield I want to know the 90% yield or 0.9, so I will calculate what should be my time. Okay. So my new retention time is 46.5, my new sigma is 0.182, okay, my yield is 0.9, so T has become now 61.8 minutes. So if you remember in the previous case, okay, so T has become 61.8 minutes with the internal diffusion. So if the internal diffusion is controlling factor, then sigma will be proportional to V raised to the power half, and when I am doubling from 30 centimeter per hour to 60 centimeter per hour, my time required to collect has become 61.8 minutes. Now let us consider another situation. The process is controlled by external mass transfer, that means the movement of the solute from the bulk to the surface because of the two phase system is controlling. So in such a situation it has been observed that sigma square is proportional to V raised to the power half, where V is your velocity, d is the particle diameter, d raised to the power 3 by 2 divided by L, L is the column length. So here it is slightly different, sigma is proportional to V raised to the power 1 by 4, whereas if it is a pore diffusion it was like sigma proportional to V raised to the power half, whereas if it is external mass transfer sigma has become proportional to V raised to the power 1 by 4. So same thing, original sigma was 0.129, I have doubled the velocity but the exponent is 1 by 4, so my sigma has become 0.153. Now again I make use of the yield equation, 0.9 is the yield I would like to have, I know the T naught is the reduced from 93 to 46.5, my sigma has changed, sigma has increased to 0.153, so I substitute them inside this same yield equation to get a new time, T is equal to 59.4 minutes. You see depending upon the controlling mechanism you will require different times for collecting your effluent to achieve an yield of 90%. Okay, let us consider another situation. Okay, now if the process is a set of ideal equilibrium stages, if you remember long time back, maybe 2-3 classes back, I talked about ideal equilibrium stages. That means the chromatography's entire column is divided into n number of ideal stages, each stage has the stationary phase equally distributed. Okay, now the continuous phase is entering from n, that is say from the left hand side, and then it is leaving on the right hand side into each stage. So from stage 1 output goes into stage 2, and from stage 2 output it goes into stage 3 and so on. So there is an interaction between the solute in each stage with the corresponding stationary phase. So there is an equilibrium in each stage taking place between the solute in the continuous phase as well as the solute in the stationary phase in each stage. So that is called an ideal equilibrium stage process. Okay. So the entire column is divided into n number of ideal stages, large number of ideal stages. So in that situation sigma square will be proportional to 1 by L, that is the column length. So if the column length is very large, you have obviously large number of ideal stages, then your sigma will become small, that means the peak width will become very small. Obviously the efficiency of the column is extremely good. If the column length is short, your sigma will be large, that means peak width also is large, that means the efficiency of the column is not so good. Okay. Now in such a situation, in an ideal equilibrium stage, sigma square is proportional to 1 by L, so velocity you can see is not coming into the picture. Okay. Now T naught is once again half of 93, that because you have doubled the velocity from 30 to 60, but sigma square will be unchanged because velocity is not coming into this place. Okay. So you take this T naught, you take the old sigma and then put it into the yield equation, and you should be able to calculate the time required to achieve the 90% yield. So when if you do that, okay. So you take your old sigma, so the sigma is the same whether it is, okay, the n number of stages where n could be anything, okay. Sigma remains unchanged here because sigma is only a function of L, it is not a function of the velocity. So the old sigma is taken, that is 0.129, but the T naught is of course gone down from 93 to 46.5 because you have doubled the velocity. So when you substitute that into the yield equation, okay, if you remember this yield equation, yield is equal to 0.5 into 1 plus error function T by T naught minus 1 divided by square root of 2 into sigma, you will get a new time, okay. So we saw 3 different situations depending upon what is controlling. We said if the bulk mass transport is controlling, that means the solute movement from the bulk of the solution to the surface of your stationary phase, or if the pore diffusion, that is the movement of the solute molecules inside the solid matrix is controlling, that is one situation. Third one we looked at is ideal situation where we are dividing our entire column into n number of ideal stages and then trying to see whether that is controlling, okay. So depending upon the type of controlling mechanism, you may have different sigma values, okay, and then you use them all in your yield equation, and when you use them all in your yield equation you will be getting different time until which you need to keep collecting the effluent so that you achieve the desired 90% yield, okay. So a chromatography column can have different types of mechanism because you have a packed system and you have a liquid flowing from one end to the another end. So you may be having a bulk mass transfer taking place from the bulk of the liquid to the surface of the particles or the stationary phase, okay. Then this particular solute gets absorbed on the stationary phase and then they start diffusing inside the pores, so that could be controlling. And if there is a reaction taking place between the solute and the stationary phase material, or if there are any ligands present in the stationary phase material which is acting as a catalyst, then there could be a reaction taking place. So all these could be controlling. And what does controlling means? When I say controlling, all these 3 may be acting in series, but one of them is the most important, rest of them may be very fast. So if out of these 3, if 2 processes are very fast and if one process is slow, so we call that as the controlling, because the other 2 processes we can assume takes place within instant of a time, whereas the third process takes much longer time to take. So with relatively it takes much longer time to take with respect to the other 2, so we call that as the controlling. So in this particular chromatographic situation we are saying that the mechanism are varied, the bulk flow, the bulk mass transfer, and then mass transfer from the bulk liquid to the surface of the stationary phase, and then there could be pore movement inside the pores, and then there could be reactions taking place and so on actually. So depending upon various situations we say that the interaction between the solute molecule and the stationary material will change, and depending upon these interactions or the strength of these interactions, the spread of these Gaussian peaks also change. So when we mention about spread, we are also talking about the standard deviation, or we are talking about the sigma. So the sigma also will change depending upon the mechanism, and if the sigma changes, obviously the peaks may be becoming broader or the peak may be becoming shorter or very tight actually. So we looked at large number of mathematical equations we also looked at various types of situations which help you in designing the type of process operations which we need to carry out. These operations could be the amount of time required to achieve 90% yield, or if I collect for a certain period of time, what is the yield of my product, and if I have 2 or more different types of solutes, if I am collecting at different periods of time, what will be the impurity levels, and so on actually. So these are very useful, especially if you are running a chromatography, and especially if you would like to know how to run a chromatography efficiently and try to get maximum purity as well as the maximum yield. Now in the next class we will continue with the same chromatography, and let us look at use of chromatography in analytical purposes. Like you must have all heard about the HPLC, the high pressure liquid chromatography or high performance liquid chromatography, which is predominantly used for only analytical purposes, where if you are interested in identifying a particular metabolite that may be present in your mixtures, it could be a protein, it could be a biomolecule, it could be a small molecule, or if you want to look at the quantity of that metabolite in the mixture, we generally go for HPLC, and it is very useful if the component is not vaporizable. That means it may have a very high boiling point, or if I heat it up it may lose its activity. Then ideally this type of analytical instrument, predominantly the HPLC, is extremely useful. So that is what we will be talking about in the next class.